All right, so in your simulation, what you have is a circular object that you could, choose which shape you want, and you can apply a force, and that force is applied tangent to the circle. Your distance pivot points are, so your net torque is a function of one force, and it's just going to be Fr. You don't have to worry about sine theta here because you have your 90-degree angle there. So if you're looking for a second law expression, the net torque equals I times alpha. Now, let's just say for the sake of argument, I chose this to be a disk. You may have chosen one of the other objects. Doesn't really matter. It's just going to change your expression for I here. For disk, it happens to be 1/2 mr squared. So we can put in Fr for a net torque here. And you know what? I actually might want to make it negative here because that's going to cause clockwise torque. So maybe having it as a negative sign makes more sense here. 1/2 mr squared in for I. Now we can solve for alpha here. Basically, we'll cancel out one of those r's, just divide both sides by 1/2 m, and I guess alpha would end up equaling negative 2f over mr. Did I say divide by 1/2 m? I meant 1/2 mr because we still have an r there. And this would end up being our value for alpha here. This is how fast it's going to pick up speed. Once you know this value, you can run through the kinematics and you can see, well, how fast it's going, how many rotations it's going to do in a certain amount of time. Once you have alpha, you can run through all the kinematics and tell me exactly what the disk is doing. We also got a negative value here. The sign of alpha is going to tell you what direction this rotates in. This is going to rotate that way because it's starting from rest. Now, there is a possibility that maybe you have more than one force, not in this simulation, but elsewhere. And I believe this is an example in the PowerPoint. But if you have one force here, F1, you have another force here, F2. Basically, what these guys are doing, despite the fact that they're both down, they're working against each other. One's trying to rotate it clockwise, the other one's trying to rotate it counterclockwise. They're both the same distance r away. So if you're doing net torque here, it is a function of two forces. That one's positive, that one's negative in terms of the torque. So I'm going to write F2r. Again, you don't have to worry about sine theta here because we have a 90-degree angle, minus F1r. There's your net torque. Let's still assume this is a disk. So then I is equal to 1/2 mr squared. And now, second law. Putting it in, you get F2r minus F1r in for your net torque. 1/2 mr squared. For moment of inertia, there's alpha. Divide both sides by r. Then divide both sides by 1/2 mr to solve for alpha. And you're going to get F2 minus F1 all over. There would be a 2 there because that 2 would come up and you get this. Now, what type of rotation you get here, it all depends upon, which force is stronger than the other. I've had it drawn where the F2 is stronger than F1, so I would expect counterclockwise rotation here. However, if F1 was greater than F2, this expression would actually yield a negative value for alpha. So it all depends upon, the size of the forces, but this expression would be applied to both forces regardless of how large they are relative to each other. All right, so you have multiple forces here. And again, if you end up just changing the shape, that's just going to change your I value that goes here. And you're probably going to get a different number there instead of a 2, depending upon, what situation you're in. But hopefully this sheds some more light into the second law of rotation. So basically you always just want to look at what your net torque is, what kind of shape do you have, and then running through that, you can figure out what alpha is. And then, like I said, once you have alpha, you might have the ability to go through all the kinematics of what's going to happen while these forces are in play.